Okay, good morning, everyone. I hope you had a good weekend. Today, we are carrying on looking at evolutionary epidemiology. We started off looking at this last week, where we were looking at pathogen evolution. We were looking at evolution of virulence, how deadly a pathogen might be to its hosts. And we also looked a little bit at the evolution of drug resistance as well. So two super important topics when it comes to public health and understanding infectious diseases, also in things like conservation and ecology as well. Today, we are going to be still looking kind of within the realm of evolutionary epidemiology, but moving on from pathogen evolution to thinking about host evolution. In my role as a researcher, I'm interested in infectious diseases and how they spread and how they evolve, but I'm also interested in how they affect host evolution as well. And part of the reason for this is that pathogens and parasites are found throughout the natural world, right? So we might think about human infectious diseases because we're humans. But pretty much wherever you look, you find pathogens and parasites. Because of this, it's such a dominant sort of, or not dominant, but a very common relationship or ecological relationship that we find in nature. And pathogens and parasites often have a really severe impact on host survival, as well as host reproduction as well. So we should generally expect that hosts have evolved in response and continue to evolve in response to selection pressure from pathogens and parasites. And they can evolve a variety of different defenses, if you like. They could have various behavioral defenses. We see examples of this, particularly in things like sexual selection and around mate choice. So maybe the reason that individuals sort of choose the number of partners that they want to mate with, or even who they mate with, might be based on sort of a little bit of strategizing, if you like, to minimize your risk of infection. There also can be behavioral things like grooming of individuals to try and remove ticks and parasites, particularly in things like, say, chimpanzees. Behavioral traits like even things like group size. There might be an optimal group size to have. If there are too many individuals crammed into a small area, it might increase the risk of infectious disease. If you don't have enough individuals, then maybe it's not very good in terms of protection against things like predation. Things like physiological defenses might be more apparent. When I say physiological defenses, this can really be things like, even things like the bark on trees could be seen as a physiological defense to parasites. Your immune responses, your immune genes and your innate and adaptive immunity as well, they have clearly evolved in response to pathogens and parasites. Okay, so, and we are not the only organisms that have immune defenses found throughout nature. So lots and lots of different ways in which hosts can potentially protect themselves or avoid infection. And generally, we try to group most of these things in terms of resistance or tolerance. Resistance, I'm also going to include avoiding infection, because they have, when we model these mathematically, they have broadly the same effects. So either basically preventing infection or dealing with the consequences of infection. Just the difference between resistance and tolerance. Okay, so we're going to focus on host evolution in today's lecture, and we're going to focus on this first one, prevention, essentially prevention of infection. So by the end of today, you should already understand essentially what resistance and tolerance are from what I've just said now. We should be able to construct and analyze and interpret some models of host evolution. So you should all be fairly familiar with this by now. This is our very simplified compartmental model of an infectious disease. Here there are just two classes, S and I, representing our density of susceptible and infected individuals. And in fact, in this model here, it's just an SI model because individuals can become infected, but they can't recover. So there's only a flow from this S to I. Okay. Again, don't know what happened there. Again, we've set the recovery rate to 0. We do this here just to kind of simplify the math again. Just to recap some of these terms here. So B of S and I potentially is our birth rate. Beta SI is our rate of new infections. So beta is our transmission rate. D is a non-disease associated mortality rate. And alpha is our disease-associated mortality rate or virulence. Okay, so previously we looked at evolution of this alpha when there was a trade-off with beta. Okay, so I mentioned these ideas of resistance or tolerance. One way of conceptualizing this is imagining that trade-offs are going to be important in this just as they were for pathogens. The hosts can't just become completely resistant or can't necessarily just become completely tolerant without paying some cost associated with that, right? Otherwise, everything would just be resistant or tolerant completely, right? So generally, we would expect there to be some sort of trade-offs. One way to think about this is thinking about resource allocation. So hosts have, they consume resources, nutrients, and so on from the environment. They have a finite amount of those resources, and they have to devote them to all of their different tasks. So, growing, cell repair, protection against disease. Okay, all of these things they might have to maintain, and so they can't just necessarily put all of their resources into resisting pathogens. Okay, so they might have to sort of balance this budget, if you like, between, say, how quickly they grow or how much of their resources they put into reproduction versus how they are able to protect themselves from infectious diseases. Okay, so if we imagine that X is just some number between 0 and 1, and that is telling us something about the strength of host defenses, where X is equal to 0 is no investment in host defenses, and 1 is complete investment. We might have, for example, our betas become, say, a function of this X. Maybe there's a baseline transmission rate, beta naught. And if we multiply this by 1 minus X, well, this is saying when X is 0, there's no investment in protection from resistance. We have our baseline level of baseline transmission rate here. When X is 1, we're completely protected. And if we're talking about tolerance, our alpha now would be a function of X. Again, there might be some baseline level of virulence, alpha 0. Again, we can multiply this by 1 minus X. Generally, we would not expect resistance and tolerance to both improve at the same time without there being some trade-off between these things. So one could explore, for example, what happens in a trade-off between resistance and tolerance. So maybe in that model, you would perhaps replace this by X here. Okay, so you could, when X is 0, maybe you're not resistant at all, but you're completely tolerant. When X is 1, you are completely resistant, but not tolerant at all. Obviously, if you're completely resistant and not tolerant, then it doesn't matter if you're not tolerant. So it's not the best of models. Anyway, the point is we can think about how these different traits evolve under different conditions. This here is for just some alpha naught and beta naught greater than 0, just for clarity. Like I said, in the absence of any trade-offs, we generally expect investment in host defenses to evolve to be maximized. Okay, so that's kind of a trivial scenario. So we always assume that there is some kind of trade-off. Otherwise, we just automatically get our selection gradient essentially would always be positive, and we would just always get selection until we maximized whatever our defense happened to be. Okay. I mentioned this idea of choosing. It's important to remember, though, when we're talking about evolution, that organisms are not choosing per se. We often use the language of sort of choice, or it kind of seems to imply agency. I said, for example, before that pathogens don't want to kill their hosts in quotes here. They obviously don't have any sort of agency over this. We're talking about random mutations on which selection acts. Okay, but often that just like when we were talking about evolutionary game theory before, it can behave like a sort of rational individual who is wanting to do such and such a thing, right? Okay, so hosts have to choose in the sense of natural selection is choosing here to invest, perhaps some more resources in birth or growth or death, resistance or tolerance. Okay. We're going to look at a little bit of a simpler scenario. We're not going to think about tolerance. We're just going to focus on resistance. In other words, preventing infection in the first place. And we're going to use our baseline SI model that I recapped at the start. And rather than this notation up here, we're just going to look at the evolution of beta itself. Okay, so we don't actually have to have this X as a dummy variable here. What we're going to do is we're going to assume that this susceptibility to infection is going to trade off with reproduction. Okay, so we had a birth rate before that was a B, going to assume that this B is a function of beta. And suppose there's some baseline B naught, which is our baseline intrinsic growth rate. This is going to be multiplied by 1 plus beta squared here. A little bit of clarity. I'm actually going to edit these equations up here ever so slightly, just so it's consistent with my notes later. I'm going to have this B of, make this B of beta times by 1 minus Q n here. Okay. Yes.
Sorry, quick question.
Yeah.
Is beta still a function of x that we're considering?
No, we're going to drop because we would basically be evolving x, but then we'd be substituting in beta afterwards. So we're just going to evolve beta by itself. Yeah. So yeah, this here is don't worry about this too much. This is basically just for consistency of notation, this particular aspect here. Okay. Okay. So you can think of this as its intrinsic growth rate is varying, but the density dependent component, which is the 1 minus Qn, is obviously just part of the, it doesn't actually feature in this B of beta. Okay, so what does this look like? And let's think about why we have this. We could take a different shape of this trade-off as well. There's no reason necessarily why we would a priori assume that our trade-off would take this shape. We're just going to take the shape for some convenience. So what does our B of beta look like? Well, when beta is equal to 0, we're just at B naught. And then this grows quadratically. Something like this. B naught. Beta is equal to 0. Baseline transmission rate. What does it mean? Well, it means that as we increase beta, what we're really saying is we're less resistant or more susceptible, but we have higher reproduction. This would be taking your resources away from resistance, diverting them to reproduction. So you're paying a cost of higher susceptibility. One thing as well to remember about this beta is essentially like a composite parameter in our models. We usually simplify it down, but you can think of this as being the product of many different things. Okay, so this beta, for example, you can think of as being, this beta is essentially some, let's call it beta 0 here, some baseline transmission probability per contact. So let's suppose this is a probability of transmission per contact. There'll be some contact rate, C. Maybe C is just some non-negative number, which is a rate. And so we can think about, because we're multiplying these things together, this is why the actual sort of physiological resistance mechanisms and behavioral avoidance mechanisms essentially behave the same in these models, because you can think of this beta naught as being something that is varying in this trade-off here. So your intrinsic susceptibility to infection, given you come into contact with someone who's infected, okay? So people, we could think about this as being actually our beta naught and is actually going between 0 and 1 perhaps, and increases accordingly. So you increase your risk of infection as beta naught increases. This would be some sort of physiological mechanism. Alternatively, you could imagine this here instead of B, this could be some contact rate C that is increasing. And beta naught may be fixed, so you have no variation in your intrinsic level of resistance. But maybe these individuals, they are, rather than being less resistant, they are less cautious in their behavior, perhaps. So maybe they're able to mate with more individuals, increase their reproduction, but at the same time, they're more likely to get infected, so their contact rate has gone up. Yes?
In this model, what is the Q value representing?
The Q value up here is just a density-dependent effect on our reproduction. So just like in the project. Okay. Okay, so the point is here, we're going to switch back and talk about this in the language of resistance. I just wanted to clarify that really, when we're talking about resistance, we can also often talk about avoidance as well, partially because of this beta being this composite parameter in our model. Okay, we can't essentially distinguish between physiological defenses like a stronger immune system versus having a different contact rate. Okay, so what are we going to do? Well, we can actually non-dimensionalize our SI model from up here. We can non-dimensionalize this model. What I mean by that is we can rescale time according to one of the rates in our system, and we can rescale the population densities as well by one of the other parameters. This is essentially the same as setting one of our rate parameters. This here I'm going to choose as B0 from our trade-off, it's being equal to 1, and I'm going to set Q as equal to 1 as well. Essentially, if you non-dimensionalize the model, you would have all of your rates up here would now be divided by B0. So for example, this D would be over B0, this B2 would be over B0, and so on. And we would be rescaling time according to some, I'll call it capital T here. And then we can rescale the population sizes. So now rather than S and I, for example, maybe we have U is equal to S, say S over Q, if I remember rightly. No, SQ. There we go. And say V is equal to IQ. You do all of this non-dimensionalization, and then your Q parameter would drop out. This is essentially the same as, without doing all of that non-dimensionalization and relabeling everything, as just setting one of our parameters, one of our rate parameters, in this case, B0 equal to 1, and our Q is equal to 1 as well. Yes.
When you were showing us how we could rescale it, why didn't you divide the first term of ds dt by B0?
This one here?
Yeah.
Yeah, this would also be divided, but there wasn't an explicit B0 written here, but yeah, it would be, there would also be a, sorry, yeah, just to make that clear, there would also be this divided by B0 as well. Yeah. Do you have a question? No. Oh. Okay. I'm kind of glossing over the non-dimensionalization stuff here because it's not super important to what we're doing here, just helps us to eliminate a couple of our parameters from our model. Non-dimensionalization doesn't change the underlying qualitative behavior of our models. We do some more of this in Math 360 if you're interested in learning how we actually go about doing that. Okay, so we're just going to set those parameters equal to 1. The question here is, do we need to use the next generation matrix to calculate the invasion fitness of a rare mutant host has susceptibility beta M? And hint here, once a host is infected, can it contribute anything to host reproduction? So let's just take a quick step back. So remember when we were doing pathogen evolution, we would end up with an additional equation that was dim dt is equal to something, right? And so we were able to just look at this equation here, look at its per capita growth rate when it's rare, that gives us our invasion fitness, okay? Now, when we've got this host population here, we've got two equations. Remember before we looked at the next generation method. So the question is, do we actually need to apply the next generation method to this model? Yes or no?
Because it's pretty simple. And with next generation, it's more for like structured population. So, I don't know. I feel like we don't.
So the population is structured. So that's the question right here. So when we just had an infection, a pathogen mutant, we would only ever have one class here. If we've got a host mutant, it's going to be born in here, and then later it's going to be infected, right? So technically, we might have two classes for our host population, a DSM-DT and a DIM-DT. So at first, you might think, okay, well, that means we need to use the next generation method to find invasion fitness. The key from this little hint here is whole point of invasion fitness, we're thinking about contributions to the next generation, right? That's why it's called a next generation method. Infected hosts in this model don't contribute anything to reproduction. Yeah. I realized, sorry, sorry, there was a slight typo in this as well. That should be an S in there. Okay, so only our susceptible hosts here are actually reproducing. There's no recovery. So there's no flow, if you like, back from this I class. We've got to be a little bit careful with these transfer diagrams because it's not just about whether those actual individuals themselves become susceptible again. It's about essentially whether they're reproducing again. That's the key thing. So if they recover, they can reproduce again. If this here, rather than S, if this was actually an S plus I, then even though they're infected, they would still be reproducing. So we'd have to capture them in our next generation matrix, okay? So I'm kind of laboring this point here because one could set up a next generation matrix and kind of go through all that process. You find that the I class never actually contributes anything back to the S class. So you could, another way of thinking about this is suppose we've got 100 different infected classes. That would make you like a massive like matrix, right? In terms of finding our next generation matrix. However, none of those sort of infected class rows are ever going to be contributing anything to the birth of new hosts. And ultimately, talking about invasion fitness for our hosts, we want to capture the generation of these new hosts. So we can basically ignore all of those. So what this means then is when we write down our mutant dynamics, we would end up with a DSM DT and a DIM DT. But we don't actually have to think about our DIM DT when it comes to fitness. Okay, we can have everything captured in this case by our DSM DT. So in other words, we can just look at our per capita growth rate here, 1 over SM DSM DT, and this will give us our invasion fitness. See later on today, that's not always the case, okay? Like I said, if there was recovery, or if our infected individuals were reproducing, then we wouldn't be able to do this. Another way of thinking about this I class then is it's like a dead end. So people get infected, they're never going to reproduce. Think of these as being zombies, if that helps. Okay, they're never contributing to host fitness. As soon as they're infected, that's it. There's no flow back. So we don't care about them essentially for calculating fitness. Okay, so we're going to jump straight now to our evolutionary dynamics and the simplification of not having any recovery and not any reproduction from infected individuals means that we don't have to actually go through the next generation matrix. We can just write down fitness very simply. We've already done our ecological dynamics analysis for this. Remember, the first stage of adaptive dynamics is always find our ecological equilibria, check that they are locally asymptotically stable, okay? So you have to do that linear stability analysis. We've already done that, so we're not going to repeat that here, okay? We know that as long as our pathogen is viable, in other words, our R0 is greater than 1, then we have an endemic equilibrium in this model, and that endemic equilibrium is locally asymptotically stable. So what's our invasion fitness? Well, our invasion fitness now of a host with, I'll refer to this as susceptibility. Yeah. Susceptibility and resistance are essentially the same thing. Remember, this is capturing our transmission rate as well, but we can think of this. What we're really doing is we're thinking about either this beta naught is evolving or this C. I'll focus on this as a beta naught. So you can think of its probability of being infected, given that it comes into contact with someone who's infected, okay? So we take our per capita birth rate, or growth rate of our SM class. So we have B times by beta M. Times by 1 minus Q N star. Minus beta M I star minus D. our selection gradient. Should all be pretty familiar with this now. Just going to be our partial derivative of W, our invasion fitness, with respect to our trait that's evolving, our mutant trait, beta M, and then evaluating that at our resident trait beta. So this is going to be beta prime of beta times by 1 minus Qn star. I realize actually above, I actually set Q as equal to 1. So I can get rid of this Q here. Q is equal to 1, remember. And we've also set B naught is equal to 1. Okay, so we would have had 1 minus Qn star, but the Q is equal to 1, so this is just 1 minus n star. And we have a minus I star as well. We're taking derivative with respect to beta m. The d at the end drops off. What's this? Well, what's our beta prime? Well, how do we define it up here? Beta prime of beta is just going to be equal to 2 b naught beta, and we've set b naught is equal to 1, so this is 2 beta. Whilst we're here, let's calculate the second order derivative. This is just going to equal 2. So here we're going to have 2 times by beta, 2 times by beta, 1 minus n star minus I star. So that's just substituting in my beta prime that I calculated just now. And then finally, if you want to work out whether our singular strategy, we haven't worked out what the singular strategy is, but we can determine whether or not it's evolutionarily stable by looking at the second order derivative with respect to beta m and evaluating everything at some singular strategy beta star. This is going to be our second order derivative of our birth function, b double prime of beta, times by 1 minus n star, which is just 2 times by 1 minus n star. And this needs to be negative in order for our singular strategy, whatever it is, to be evolutionarily stable. So the question then is, we haven't actually found our singular strategy, but can we determine anything about its potential evolutionary stability, given the, assuming we were to find it realistically, probably numerically. You can do this algebraically, but finding the equilibrium becomes a little bit messy and substituting it in. Okay, so we're going to just do a sort of a limited analysis here. Okay, so can we deduce anything about the sign of this, even though we don't know what our singular strategy is? Sorry, there should also be a beta star up there. Let's have a think. Well, we know that our infectious disease is always going to reduce the population size, right? It's never going to increase our population size because it's killing hosts. So let's see what our maximum population size is. So suppose we're at our disease-free equilibrium, DFE. We're just going to ignore evolution for now. We're just thinking about what is our resonance equilibrium, DSDT. You have B of beta times by, we're going to be at our disease-free equilibrium, so we'll call this S star. Times by 1 minus S star. This 1 minus S star, this is just our 1 minus Qn star, our density-dependent term, that Q is equal to 1. And because we're at our disease-free equilibrium, no infection around, so N star and S star are the same thing. And then we're not going to have any infections because there's no infections around, so our beta SI term is just equal to 0. We do have natural mortality minus D times by S star. As we're at an equilibrium, this must equal 0. Okay, because we're at a disease-free equilibrium, we know that S star is non-zero. Therefore, we just divide through by S star. And then we can rearrange this to get S star is equal to 1 minus D over B of beta for B of beta greater than D. In other words, our births have to be greater than our deaths. Otherwise, our population is going to die out. So what is our maximum population density in the absence of disease? Theoretically.
1 minus D over B minus.
Yeah. So our maximum would be 1 minus D over B naught. That's without any evolution, right? But suppose, suppose there were no deaths here, or the deaths were negligible and the births went off to infinity. Our maximum this could ever be, regardless of whatever parameters we're choosing, is just going to be 1, right? So this is always going to be less than 1. So what does that tell us then? Well, what can we deduce, therefore, about our evolutionary stability? If the maximum population size, even in the absence of disease, it's always going to be less than 1. What's it tell you about the sign here?
It's not going to be evolutionary stable.
Yeah, so this second term here, the 1 minus n star, is always going to be positive. That means that even though we don't know what any singular strategies might be, we can deduce immediately that they have to be evolutionarily unstable. It's never possible for them to be evolutionarily stable. Okay. So our E is equal to 2 times by 1 minus n star. This is always going to be positive. No evolutionary stable singular strategies. Can anyone tell me then, can anyone remember what possible types of singular strategies we might have? Remember there are 4 types of singular strategies. Can anyone remember what the ones are that are not evolutionarily stable? Yeah. And the other one? Yes. Okay. So we just choose arbitrarily different parameters for other parameters in our model. In fact, we don't have this A in here at all. We just choose values for D and for alpha, various mortality rates. We can generate a pairwise invasion plot that looks something like this, perhaps. Here, our plus regions, our gray regions are where our mutant invasion fitness is positive, and the white regions are where it's negative. So what I want you guys to do is to consider and discuss with a partner, preferably, what you think will happen to our beta. How does this evolve if we have these different initial conditions? What I'll do is I'll copy these up here. So it could be 0.4 or 0.6 or what did I put down here? 0.75. Okay. Just take a couple of minutes and discuss what you think is going to happen based on this pairwise invasion plot if we have these different initial conditions. Okay, let's step through these. So suppose we start off initially at beta is equal to 0.4. So we start off down here. I'm just going to zoom in just for a little bit of ease of sketching. So remember, because remember when we evaluate our selection gradient, we're evaluating this when our resident and mutant traits are identical. So we're always interested in essentially what's going along, this main diagonal here. So along this main diagonal. Your mutants are appearing in this narrow band around this main diagonal, okay? So suppose we have a mutant that has a slightly lower trait. Let's practice here. It's a slightly lower trait. It has negative invasion fitness, so it can't invade. It has a slightly higher trait value, it has positive invasion fitness, so it can invade, and it replaces our current resident. Let's repeat this process, and eventually you'll staircase into this singular strategy here. Okay? Key thing is what happens when we get there. Well, at this point, mutants above and below both have positive invasion fitness. So in other words, we've already established all of these singular strategies are going to be evolutionarily unstable. So we converge towards this, and once we get there, it's evolutionarily unstable. So what type of singular strategy is this?
Branch.
A branching point, yeah. So this is a branching point. This is where our pairwise invasion plots break down in terms of predicting what happens going on, right? So they can only tell you what happens going up to a branching point. At this point now, we're no longer in just a two-dimensional sort of plane here with one resident and one mutant. We've now increased this to we have two residents because we have mutants able to invade on either side and coexist. Okay. So at that point, we've got a branching point. We won't be able to tell from this what goes on next.
So
Yes.
once it goes up or down, it'll still come back in though.
It won't. No, these things will diverge.
But like,
Because basically,
if you go down, it'll go towards the left again.
but that's where this pairwise invasion plot breaks down. So this pairwise invasion plot only applies for when there's one resident and one mutant. As soon as you can almost think of this as being like, we're starting off, we're evolving kind of this along this table as a plane, right? And then as soon as we've had this, the fact that we can have these two types, we're no longer in this two-dimensional plane, we're now in a three-dimensional plane, right? We've say got one mutant invading and there are two residents. So we've moved off the surface of this table. So this pairwise invasion plot is a 2D representation, but we're now in 3D, so it doesn't actually work anymore. Okay, so that's why it only works for branching points up to the point where you get there. And then we can tell because you can draw a vertical line through this singular strategy where both sides above and below are in this gray region. That means it's a branching point. Okay, if you'd chosen 0.6, suppose you started off up here, beta would have decreased. So it's still convergent stable. We're going to tend towards this branching point here. Okay. The same long-term behavior will converge to this point and then branch. What about if we start off at beta is 0.75? Yeah.
Like, I think it will just like the mutant will just like cause the beta value to like just increase on the staircase.
Yeah, exactly. So we're just going to keep stepping this way. Here, I've happened to have terminated it at 0.8. There's nothing up. This is sort of arbitrary here. This would just tend off to infinity. Yeah. In reality, we wouldn't be able to have infinite rates here. If we had actually converted this to be our probability of our susceptibility, if you like, and it went between 0 and 1. So 1 would be you're completely susceptible, you have no defenses. Then this would just go up to 1. If we were actually dealing with something like our contact rates here, then it would go up to whatever our maximum contact rate would possibly be, due to constraints within the system. Okay. Either ways, this goes up to whatever maximum we could possibly physically obtain.
Yeah, I have another question.
Yeah, go for it.
Like, does the second intersection point around like 0.7 with beta resident value, would that also be like a technical branching point there?
So this is not a branching point because it's not convergent stable. So we can see either side here that you step away, right?
Yeah.
So this is evolutionarily unstable and convergence unstable.
Okay,
So this is a repeller, yeah. So we've got a branching point and a repeller. So this one down here is evolutionarily unstable, but is convergent stable. We haven't actually analytically shown that it's convergent stable, but we can see from this pairwise invasion plot what's going to happen, okay? This is probably something I would expect you to be able to do on an exam, hint. I don't think I can give that much more of a figure. It's the kind of thing, it might appear, it might not appear. I'm just going to say it might. So being able to interpret a pip is something that I would probably expect you to do, okay? So we've already discussed this. I'm not going to write this all in, but we have a branching point at around beta is 0.45 and a repeller at around 0.68 roughly. Okay, what I want you to do now is again chat with your partner. Suppose we're going to start at beta is equal to 0.6. We've already sort of mathematically described what's going to happen. Okay, we're going to converge to this branching point, and then the population is going to branch. Now imagine you're not talking to a mathematician, you're talking to a biologist, doesn't know anything about adaptive dynamics and branching points and things like that, or what convergent stability is and so on, and evolutionary stability. What I want you to do is to try to describe that to them. So describe what happens if we start off here. Try to describe this to someone who doesn't have a mathematical background, who's a biologist, so they should understand the biology side of things. How would you describe this? This is the sort of interpretation step of modeling. Okay, so again, take a couple of minutes, chat with your partner. Okay, everyone, time is a little bit short, so I'll go through this. So any ideas on sort of describing what's going on here? So we're starting off initially at the purple dot here. How would you initially describe what's happening in a biological sense? Yeah.
The infectivity goes all the way down.
So
to-
that's just like as a first stage, right? Initially, we're going to assume that our host, or sorry, not assume, our host evolves a lower susceptibility, or ultimately just the transmission rate goes down, whether that happened to be through resistance or through changes in contact rate. Ultimately, this decreases, right? So that's just like your first stage. So we can say initially we would expect that our hosts would evolve to say be more resistant. Okay, stage one. Okay, stage two. What happens eventually? Like, if something is becoming more and more resistant, either eventually it's going to become, tending to some sort of limit. We can't kind of become forever more resistant, if you like. So what happens then?
Our birth rate, reproduction rate is going to become lower, so it doesn't benefit them more to become more resistant.
Yep. So there's some trade-off here. Yeah.
And either way, some hosts choose to become more susceptible and have higher reproduction rate.
Mhm.
And some choose to become more resistant and have less reproduction rate, and they both coexist. They both have. Then the dynamics is going to change after that. They're gonna coexist.
Yeah. So we evolve to a higher level of resistance, but eventually the trade-off becomes sort of too costly. And so now our population diversifies into two contrasting strategies, like one that we could show, because one of these is essentially going to be increasing its transmission relative to this singular strategy. One of them is going to be lower. So we're on one on either side of this singular strategy. So one of them will increase its transmissibility, but will also increase its birth rate. One will continue decreasing its transmissibility, or in other words, increasing its resistance, and therefore decreasing its birth rate. So kind of, you see these two contrasting strategies or lifestyles that can end up coexisting here. One of them with hosts that sort of prioritize their birth rate and kind of risk infection, and ones that prioritize protecting themselves and not being infected, but paying the cost of having a lower birth rate. And kind of see how these two things might be able to cancel out, essentially, because if they're coexisting, then one can't be fitter than the other, right? So we've got these two contrasting strategies. Yeah.
Is there a case where, okay, there's a branching point, we have two different strategies, and once two of them are coexisting, they do not coexist for so long, like the dynamics is changed, so we can't use this, but in that, if we analyze those differential equations, we see, okay, one of them is going to become extinct again, and we're going
exactly. That is definitely possible. You can see this in some of the models. We won't get time to explore those, but that is definitely possible. They could keep diverging until a point where one of these strategies goes extinct, at which point maybe the first one comes back, and you can actually end up in a kind of continual cycle where they diversify, one thing goes extinct, gets pulled back to the branching point, diversifies, that one goes extinct, and you can kind of go for this sort of oscillating motion. So you can definitely see that. Good question. Okay, almost at the end now. So I just have some more material I wanted to go through, but I'm just going to very briefly summarize this. What I would actually encourage you to do is to have a little bit of a practice of the method here. Okay, so although the printed notes will be online, have a go at working through this yourself and then compare to the printed notes just for practice. Okay. The point of this last model that I wanted to go through is just to say, kind of going back to what we discussed at the beginning, do we have to use the next generation method or not? This here is an example of what a model where we would have to use the next generation methods. It's very similar to what we had before, but now we have this gamma term here. So there's recovery here. Note that we would also have to do this if we had something like S plus I here rather than S, because our infected individuals would be producing new hosts. Okay, so here infection is not a dead end anymore. So now when we write down our invasion dynamics, we have to account now for in the next generation. So for our invasion fitness, has to account for susceptible individuals who are producing new susceptible individuals. We also have to account for infected individuals who, during the course of their lifetime, will go back and produce more susceptible individuals. Okay, so they're not producing them whilst they're infected, but they could recover in future. Okay, so we should expect a certain amount of flow, if you like, back from this IM class into this SM class, which then allows them to reproduce. Okay, so now we would have to, because they're able to recover and reproduce again, we have to account for this. Okay. So now in our invasion fitness, we would look at our Jacobian, and then we need to decompose this. Think about what these decompositions are like. And then when we actually, this is our model from before with no recovery, and our pairwise invasion plot that we had before. In this particular model, we find that even a relatively small amount of recovery can have a sort of a structural effect on our model. So a relatively small amount of recovery here essentially moves, you can see this curve here. This kind of gets pushed down, and these two, this is something that is convergence unstable, and this is something that's convergence stable. They meet and they annihilate each other. So this is a bifurcation in an evolutionary sense, if you're familiar with dynamical systems. Okay, so they come together. As this curve pushes down, they get closer and closer and closer together. They annihilate each other. Now we end up here in a situation where you just always get selection for higher beta. Okay, it would never be advantageous to have selection for lower beta. Okay, that's it for today. On Wednesday, we are going to be exploring co-evolution. We've talked about host and pathogen evolution separately. We're going to be thinking about them briefly, how they co-evolve together. I've already sent out an announcement next Monday. The class is cancelled. Please use this time wisely to work on your projects. And then the following Wednesday will be our last lecture, which will be a course review. Please come armed with some questions, if you have any, ahead of the final. Okay? Great. Have a good week. I've got office hours now.